rotational motion to linear motion. So when we were brainstorming different ideas and designs, the first thing that came to mind was the 201 Stirling engine, which essentially had a piston and a rotational motion that was controlling that. And so very similar to that, we came up with the crank, link, and slider design, which, as pictured, basically you have a red arm that attaches to the gray motor arm, and that red arm attaches to like a block peg that's yellow, and it can slide through that. So the first thing we did was we essentially calculated the RPM of the motor because we weren't supposed to trust what the box said, and so we didn't have access to like a tachometer or any device that can track RPM. So instead we just put it up against a cardboard box and we ran the motor and we recorded that sound. And after putting it into an audio program like Audacity, you can see how long it takes for between each peak and trough, which is when it hits the box, and that gives you the time per rotation, and we got around 0.058 seconds, and then we can convert that to minutes and then convert it to get RPM, which we got as 1021, which is only about 18 RPM less than what the box said. So once you have RPM, you can convert that to angular velocity by multiplying it by 2 pi over 60. And then you can convert angular velocity to tangential velocity by multiplying by the radius of the motor arm. So once you have the tangential velocity, you can use a little bit of trig to calculate how that tangential velocity correlates to linear velocity along the peg or the accelerometer. And you find that that velocity is equal to cosine of 90 minus theta times the tangential velocity. And then to find the acceleration in that direction, you can just calculate the derivative with respect to the input angle, and ultimately you get that linear acceleration is equal to sine of 90 minus theta times the tangential velocity. So one of the main tasks of the design brief is to calculate the position of the peg, essentially, with respect to the angle in which the motor is rotating. So we had to do a little math here, a little trig. So according to this picture, we have essentially the radius of the motor arm, R, and the length of the red arm, L. And so it can create some right triangles here, and so you have theta as the independent variable. And essentially you want to find what x is, which is equal to x1 and x2. And you can use trig to isolate or to find x1 and x2 with respect to all the variables here. And so we found ultimately that the position of the peg where the accelerometer is going to be attached to is equal to cosine of theta times r plus cosine of the inverse sine of the sine of theta r over L multiplied by L. A little bit complicated, but R and L are going to be knowns, and theta ultimately is going to be the input, and then you can find what x is.